Hello dear students, welcome back to power system class. In previous lecture we have started a new brand new subject, power system 2, which is targeting the 6th 5th semester of electrical engineering GTU. In that we have started the first chapter, in which we have discussed about the single phase circuit power and about the active, reactive and apparent powers. So now continuing that, let's discuss about the power triangle first, and then we will move forward. So here you can see in this image on the left, it is drawn for the leading power factor composition. On the right is for lagging power factor composition. uh, there is no much difference in both of them, just they both kept rotated after converting in mirror image. So what is the uh, what is the formula for active power? So active power P is given by P is equal to Vi into cos phi. Here V and I are voltage and current, and phi is the phase difference between voltage and current. In this diagram, phi will be somewhere around here. Okay, so based on that, what will be the value of the cos phi? Right, cos phi will be P upon S, right? So that was for active power. Now about reactive power. Coming to the reactive power, it is represented by Q, and the formula of reactive power is Vi sin phi. Again, given phi is here, what will be the value of sin phi? It will be Q upon S, right? Q upon S, and you can verify it based on this formulas as well. The apparent power is called S, and the formula of it is simple multiplication of voltage into current, right? To verify what I've said just now, you can what we can do, we can take the ratio of uh, P and S. You can see, if we take ratio of P and S, what we will get? We will get Vi cos phi divided by Vi. So Vi will get cancelled, and remaining part will be cos phi. Cos phi is nothing but our power factor, and it is given by P by S. Similarly, we can do for Q as well. We can take a ratio of reactive power and apparent power. So Q by S equal to Vi sin phi divided by Vi. Vi will get cancelled, and we will left with Qs divided by S, which is nothing but the uh, value of reactive power sin phi. Okay, and similar things will be there for lagging power factor. The uh, only difference that we have in leading and lagging power factor is, in leading power factor, current is leading the voltage by some certain angle phi, and in lagging power factor, current is lagging from my voltage vector at certain angle phi. Again, same, right? Now let's come to the discuss about a few things about reactive power. So majority of the electrical machines, like call it transformer, induction motor, majority of these machines are using reactive power only. Not reactive power, they are using electromagnetic energy conversion principle, like Faraday's principle of electromagnetic conversion, right? So they are basically working on that principle only. And this principle, the principle itself involves electromagnetic and their functioning, right? And this electromagnetic energy, it is produced because of the reactive power. Okay, now we will be discussing about the power balance, balance of the reactive power. Okay, reactive power, by the way, is also called the complex power, because if you have seen, if you have attended the previous class, what we have discussed in previous class, uh, we have seen the value of apparent power in the form of complex number, in which we have seen S is equal to P. Let me show you here. And what we have seen, S is equal to P plus JQ. Okay, here S is equal to P plus JQ. See, and because of this, JQ is uh, complex component of this complex number, we call reactive power complex power as well. Okay, so the power balance in reactive, to understand the power balance in reactive or complex power, what we will do, let's consider a circuit, a basic AC circuit, in which load is connected at the end. Okay, simple transmission line model is model we are taking, and we are connecting the load at the receiving end side. Okay, and remember that we are considering this load to be RL load, like we are assuming it. Okay, so load is designed to operate at specific band of voltage. What band of voltage you say? So specific band, or in the term which you can understand is specific at specific voltage regulation. Okay, so the voltage regulation of this load should be in specific some limits. Okay, and the flow of the reactive power will decide the magnitude and phase of the receiving end voltage. Okay, now what is the formula of the reactive power? Reactive power's formula for this circuit is given by this formula: QR equal to Vs VR divided by X cos delta minus VR square divided by X. Okay, it is somewhat similar what we have derived in the previous lecture. If you have if you can see, if you want to attend the previous lecture, you will be seeing the link uh, above in the I button. You can click it and see the last lecture, and that we have discussed about that, and we have derived this formula. uh, Vs is nothing but the sending end voltage, Vr is receiving end voltage. Okay, X is the reactance of my transmission line, because we are taking transmission line model here, and this delta is the angle, delta is the angle between V and I. Okay, so the receiving and reactive power is given by QR, and here is the formula of that. Okay, and this angle cos delta, we try to keep it as minimum as possible, because less the value of the delta, then uh, cos delta will be close to R. If you remember, value of the cos 0 is 1, right? So lesser the value of delta, the value of the, as close the value of the delta is, then we will getting maximum cos 5, or uh, highest power factor, which is desirable for our circuit. Okay, so uh, that is something we want all the time, but we cannot always take the value of cos delta is equal to 0, because practically it is not possible. We can compensate it, we can try to make it as close to 0 as possible, but it is not possible in the real life scenario. So to make that possible, like to do that, to maintain this voltage within permissible limits, what do? At the receiving end, we use some reactive power components for reactive composition. Okay, for reactive composition. So for this reactive composition, what do we use? So uh, if you remember, in the fourth semester you have studied in power system 1, for reactive power compensation, what do we used to use? There were there were three types of compensation devices. First one, in which we use shunt capacitors. Other one is which we use reactors, and the third one which we use synchronous condenser. If you want to learn about them in detail, uh, you can access my playlist of power system 1, in which we have discussed about all three of them in detail. Okay, so you can visit them from there. And then, now coming to the reactive power, coming back to reactive power, So we use this compensation devices for reactive power, to restrain the reactive power. Now the reactive power formula for this devices, like the reactive power which will be received, will be derived from this devices, will be as per this one: QC is equal to P 10 phi 2 minus 10 phi 1. Okay, here P is our reactive power, Q is the compensated reactive power, QC is the compensated reactive power, and this phi 2 and phi 1 are, the phi 2 is power factor angle with compensation. Okay, phi 2 is power factor angle with compensation. We have compassionated this angle. We have tried to make the angle as close as close to zero as possible. So this Q2 is, after that composition takes place, the angle after the composition take place is phi 2, sorry, not Q2, phi 2, and phi 1 will be the power factor angle without compensation. Okay, before the compensation took place. Now because of the load at receiving end, okay, because we discussed in the beginning of this lecture only that the load we are considering is having reactive nature. Okay, and the power factor of the system, because of this reactive nature of the load, will be decreased, will be low. Okay, and because the decrement in the power factor, what will happen, the reactive power, the more reactive power will be supplied. Okay, there will be more reactive power will be supplied from supply side. Okay, and what will this reactive power compensation device will do it, this device will maintain the power factor at a load side with specific limit, and thus the load power factor will improve. Okay, and the reactive power from the supply side will decrease. Okay, so as we said, we use shunt capacitors, right, and synchronous condenser and reactors. So if we are using shunt capacitors, then what will be the rating of the capacitor or inductor? Inductor are used in the reactors, right? So what will be the value of it? So it is decided using this formula: QC is equal to C is equal to QC divided by 2 pi f into V square. QC that we have calculated, right? Compensated reactive power QC we calculated in the previous slide, and then 2 pi f, the f is the supply frequency, into square of the voltage, V is system voltage. Similarly for the reactors, for my inductance value, what will be the formula? It will be V square upon 2 pi f into QL. Here QL is again reactive power of the load, and uh, here QC is reactive power supplied by the reactive power compensation device. Okay, now to maintain good stability of this system, to maintain good stability of the system, as I've said, the angle, power angle, should be as less as possible. The lesser the power angle will be, the better the power factor of this system will be. Okay, so if we uh, take the value of this delta as close to zero, imagine if we took it to almost zero value, then what will be the formula, what will be left with coming here? If cos value of the cos 0 will be 1, so we will be only left with VSVR divided by x minus VR square divided by x, right? Now if we rephrase it, we will get value of VR square making VR square the subject, we will get VR square is equal to Vs VR plus Q QR into X. And based on that formula, from that equation, if we use the formula for finding roots, you might have studied that formula in your mathematics class, calculus class, that d is equal to b square minus 4ac, and the root will be b plus or minus under root of d divided by 2a, right? You might have studied that formula, that d is equal to uh, v square minus 4ac, and your root will be b minus under root of d divided by 2 into a. Okay, so in our case, what is the value of a? Value of the a is nothing but 1. Okay, what is the value of b? Value of b is vs, and value of c is qr into x. If you put that formula here, we will be get the value of vr as this. Vr is equal to vs is nothing but rb minus under root of vs square minus 4x qr. 4x qr, what is qr? Qr is our c. Okay, and 4 was in the formula, divided by 2 into a is 1, so divided by 2 only. Okay, now qs and ql we have seen in previous slides. What are qs and ql? Qr is something new to you. Qr is qs minus ql, the uh, difference between supply side reactive power and the demand side reactive power. That difference is called qr. Now, one thing I want you to remember every single time when we discuss about the reactive power, that reactive power always flows, always remember, reactive power always flows from higher magnitude to lower magnitude. Okay, reactive power always flows from higher magnitude to lower magnitude, and and active power always flows from higher phase angle to lower phase angle. That is something you always need to remember if you want to make the career in the power system domain. Okay, so reactive power will always flow from higher magnitude to lower magnitude. Coming from that, if we have QL is equal to QS, which means the reactive power from the supply side is as same as the reactive power from reactive power that is in demand, then the supply and voltage and the receiving end voltage will be same, right? Which means your system is completely in balance, you don't have to worry about anything. But that is never the case, right? Again, if QL is equal to QS, then supply voltage and receiving end voltage will be similar, equal, and QR will be 0, because what is QR? QR is nothing but the difference between QS and QL. If they are same, then QR is equal to 0. Okay, which is very good case. Now, if your QL, your load side reactive power, exceeds the supply side reactive power, if your QL is greater than QS, then what will happen? Your QR will be negative. Okay, which is almost desirable every single time. It is desirable almost every single time that QR to be negative. QR is nothing but the difference between um, the supply side reactive power and demand side reactive power, demanded reactive power and demand. Okay, so it is always feasible to have the negative value of QR. And when that will happen, what will happen? That VR will be less than Vs, because remember I've said reactive power always flow from higher magnitude to lower magnitude. Okay, so VR will be less than Vs. Okay, because QS is supply side, uh, QL is loads. QL is, you can say, load side, right? So it will which will mean VR will be less than Vs, which means reactive power is flowing from QS to QL. and QR will be negative, which is always always desirable case. Now taking the third scenario, when QL will be less than QS, when load side reactive power will be less than supply side reactive power, which means QR is positive, that resultant reactive power is positive. And when this happens, what will happen? VR will exceed the VS, which means the voltage on the receiving end will be greater than voltage on the sending end. Okay, which is never expected, because what will happen when this voltage at the receiving end will exceed the voltage at the sending end? What will happen? It will uh, put a good amount of stress on the insulation layer, and it can cause severe damage on the load equipments. And because of that, your there can be tremendous hazard on the load side, right? It can damage the load, so it is never desirable. The case which is always encouraged to obtain is, we use second case, where receiving end voltage is always less than sending end voltage, and the value of QR, the resultant reactive power, is negative kVA, is in negative kVA. KVA is always, remember, reactive power is always measured in the kVAR, that is the unit of reactive power, kVAR or kilovar. Okay, active power is always measured in the watt or kilowatt. So that was all about reactive power compensation. Now coming to the balance of the three phase system, that uh, every three phase system, it is always desired that it is always desired that all three phases are sinusoidal in nature. They always must have equal magnitude, their frequency always be equal, and the phase angle between two phases should always be 120 degrees. Okay, phase angle between two phases is always should have been 120 degrees. When all these conditions get satisfied, your phase system will be called balanced three phase system. Okay, now here you can see in the formula that uh, value of VR will be Vm angle 0 degree. So here you say, what is the Vm? Vm is the magnitude. Okay, and you can see Vm magnitude is the same in all three of these phases. See, this is VR, Vy, Vb, Ryb, for all three phases we have same magnitude. Okay, now here come for the phase angle. Phase angle is 0 degree in the first one, minus 120 degree in the second one, and minus 240 degree in the third one, which means the phase angle between between two phases is 120 degrees. Okay, 120 minus 0 equal to 120, 240 minus 120 equal to 240 minus 120 equal to 120, and minus 240 and 0. When we talk about complete rotation, we consider this 0 as 360. So 360 minus 240 is also equal to 120. So the phase difference is also equal, and the frequency or omega t, it will always be equal. Okay, so uh, I understand that frequency is not given in this formula, but here you can see that the frequency of all the waveforms is identical, similar. See, and they are 120 degree phase shifted apart from each other. Here you can see, and the magnitude, you can see that they are all three having same magnitude. The frequency is, here it is completed 360, then this one is completing 360 over here, because it started 90 degree before 120 degree before it, so it is completing 120 degree before it. This one is started 120 degree earlier, So it is completing its one rotation 120 degree earlier. See, let's first talk about VR. This is the waveform of VR. Here we are completing one complete rotation or one cycle 360 degree. Okay, now let's come to Vy. Here, starting from here, and where is it ending? See, this one is also ending at 360. Then Vb, it started from here and it is also ending at 360. See, they are 120 degree apart from each other. So uh, the the position of the waveform may not be at same place because they are 120 degree apart, but the cycle they are finishing at 360 degree only. See, after here the same sequence is repeating for Vb. See, it started from here, it ended from here. Similarly, Vr, it started from here, it ended here. Here, from here onwards, it is repeating the same sequence. And here, for Vy, it started from here, it ending on here, and from here onwards, it is repeating the same sequence. Okay, so that was the waveform or phasor representation of a balanced three-phase system. Now let me show you the phasor diagram of the same phasor diagram of the balanced three-phase system. This is the phasor diagram of the balanced three-phase system. You can see Vr, Vb and Vy. All three have same magnitude here. Okay, the length of the vectors are same and they are 120 degree apart from each other. Here you can see the angle between Vr and Vb is 120 degree. Between Vb and Vy is 120 degree and Vy and Vr is 120 degrees. So they are 120 degree apart from each other. The phase sequence considered is anti-clockwise, as you can see. First we are having Vr, then Vb and then Vy. Okay, so it is anti-clockwise. Okay, when we have phase sequence anti-clockwise, at that time your phases RYB will come in clockwise. First R, then Y, then B. This is short trick to remember. When we are having phase sequence anti-clockwise, at that time R, Y and B will come in clockwise direction, R, Y and B, and the vice versa for the clockwise. Okay, just always remember not to mess things up, like first writing Vr here and then writing Vy here and then writing Vb here and then mentioning that facing was anti-clockwise, because that would be false. Okay, and based on this diagram, can't we say one thing, that the sum of this all three voltages, because they are having same magnitude and same frequency and they are 120 degree apart from each other, so the sum of all three of these voltages Vr, Vb and Vy will be always equal to 0, right? The sum of the instantaneous voltage is 0, and always for the any three phase system which is in complete balance, the sum of all these instantaneous voltages will be 0. So always try to remember that. Okay, and what is balanced three phase power? Okay, so balanced three phase power is nothing but, let me say that for the balanced three phase system, the power which is consumed by all the phases, the power which is consumed by all the phases R, Y and B, R, Y and B, the power which is consumed by all the phases must be identical. Okay, which, what does it means? It means the active and reactive power for all these phases should be similar or equal. Okay, although we all know that that condition is almost impossible to achieve, it is very difficult to achieve that goal, and that is why we are having this compensation devices, right? Because load will never be the similar on all three phases, right? Load will always be diverse in nature. Okay, because if you have given supply to one colony with R phase, and then other colony from B phase, the other colony from Y phase, then there is no chance, there is no possibility that uh, the load which will be consumed by the power which will be consumed by the load will be identical. So because of this diverse nature of the load, we are having external compensating devices which we have seen just a moment ago, like shunt capacitor or shunt reactors or synchronous condensers, right? So these are external compensation devices which we use to maintain the power factor, and to keep our three phase system in balance, three phase power in balance. So that is the balance of three phase power. So we will be keeping this lecture till here. From the next lecture onwards, we will be discussing star and delta connected loads, and the transformation between star to delta transformation and delta to star transformation. So we will keep this lecture till here. Thank you for watching. I will be seeing you in the next lecture. Thank you. Bye bye.